This is video 68 in our series on tensor calculus. In this video, we'll take a closer look at the Christoffel symbol. In the process, we'll see that we have to modify its definition to make it generally applicable for surfaces and curved manifolds. In video 28, we introduced the Christoffel symbol. That's this factor right here. We said the Christoffel symbol is just a set of scalar functions that can be used in conjunction with our covariant basis vectors here to form linear combinations that in turn represent this side of the expression here. This is just our partial derivative of our covariant basis vector with respect to the coordinate value zj. And that, of course, is a vector. So this vector is represented as a linear combination using our Christoffel symbol. Well, we know that this is valid for Euclidean spaces, and because of that, we know that the form of this expression is also valid for a simple plane. If we have a manifold that's just a simple flat plane, then this expression works as well. So that means this expression works. It's the same expression, it's just that I'm using surface coordinates here instead of the three-dimensional coordinates up here, and I'm using the surface indexes, the Greek letters here. So the same concept works in both cases because we're dealing with Euclidean space. Now what we want to do in this video is ask the question, does this simple form, this one down here that we know works for a plane, does it work for all surfaces in general, even if they're curved? And the simple answer to that question is no. We're going to discover that we have to make some extensions to this expression in order for it to work for curved surfaces. Now, to understand why that is the case, let's look at this diagram. This is a diagram of a curved surface that I've drawn in this yellow outline here, and on it I've drawn a single coordinate line for S1. And then I've also drawn the covariant basis vector S1 as well. And of course you know that that basis vector has to be tangent to our coordinate line here. So let's talk about what it means to take the partial derivative of S1 with respect to S1 here, effectively carrying out this operation. And let's look at what it means graphically to take that partial derivative. Well, if we're going to take the partial derivative, what we're going to do is we're going to move a point along our coordinate line. We're going to bump this point along to a spot, say, right here. And this distance that we move from here to here is just a delta S1 value. It is the change of our coordinate S1 as we move this point along the coordinate line. And of course, as we do that, the basis vector moves along with it, and it has to remain tangent to our coordinate line. So that means it's going to point off in this direction. It has to remain tangent to our coordinate line. And because the coordinate line is curving, then the vector, S1 vector, has to change in its direction. So if we look at it this way, let's draw a parallel vector right here. I'll use dashed lines for this. This is a vector that is parallel to, equal to, the original S1 vector over here. So the change of our vector as we move S1 from here to here is this little line right here. So this is the change, the delta S1 value of our vector that's changed. So what we're doing in taking the partial derivative is finding the ratio of this change of the vector with respect to the change in the coordinate, and of course we're finding the limit of that as S1 goes to 0. Okay, now here's what we're getting at, is that if all of these lines were in a plane, if our coordinate line was in a plane, then our basis vector might move to the left or right because our coordinate line might move left or right as it winds its way through the plane. But it would remain in the plane. Because our coordinate line is in the plane, it can only turn left or right, and therefore our basis vector can only turn left or right. And that means that whatever the new value of our basis vector is, it's going to be in the plane itself. Now, you'll also recall that this kind of expression over here using our surface covariant basis vector can be used like this to represent any vector that lies in our tangent plane, but it cannot be used to represent a vector that does not lie in the tangent plane. Well, if our surface is a plane, then we're okay here because, as we said, the basis vector is going to stay in the plane. But if we've got a curved surface in which this curvature is part of the space itself, then notice how this change of the vector has actually introduced a normal component. It's actually pointing downward here. In other words, our change of our vector here has produced a vector that is no longer in the tangent plane. So in order for that to work, we're going to have to add an extra term here. This term can only be used to represent the component of our vector that lies in the tangent plane. Well, if it's a vector that's general in nature that may not lie in the tangent plane, then we've got to add a term that includes our normal. So I'm going to add this term. So we need to add a normal component with some sort of scalar value here that represents the magnitude of our change of this vector in the normal direction. Okay, well, however, remember that what we have here is an equation that's not just a simple equation, but it's an equation with two free indexes. In other words, we're dealing with four expressions here. Alpha can be 1 or 2, beta can be 1 or 2. So with two free indexes, we've got four relationships represented here. And that means in order for this to work, we have to carry those indexes over to our new term. In other words, I've got to add alpha and beta right here to maintain the consistency in the proper syntax. And what that really means is I'm adding a scalar value, a scalar component to our normal, but I'm adding a set of four of them, one for each of the four possibilities of alpha and beta. Now, what we've done here should remind you a lot of what we were doing back in video 65. If you remember back there, we said if we have a general vector that may not lie in the tangent plane, just a general vector that may point in any direction, we represent that in our tangent space by decomposing it into a surface projection and a normal projection. So that's all we've done here. We've said that this result may be a vector that points in any direction, not just in the tangent plane. And if we're going to represent it in our tangent space, we have to use this kind of form. We use these surface covariant basis vectors to represent the linear combination that gives us the component that is the surface projection, and then we use our normal here with a scalar value to represent the normal component. And together, this is the representation of a general vector in our tangent space. So that's all we're doing here. Okay, so let's take a few minutes then to focus on our new term right here. Well, first of all, I'll say this, that this new factor, this b alpha beta, has a name, and we call it the curvature tensor. And what we're going to find is the curvature tensor plays a pivotal role in our analysis of curved surfaces. We're going to see this factor b alpha beta show up many times in future videos. Okay, so let's take a few minutes to see if we can derive some basic properties of this new object, this curvature tensor. Well, first of all, I said it's a tensor, so how do we know that it's a tensor? Well, we can see that pretty quickly simply by using our quotient theorem. And here's how we do that. Over here, we know this is a vector. We know this is a vector. It's a linear combination using a known vector and scalar quantities. So let's subtract this term from both sides, moving it over here. So we'd have a vector minus a vector, which of course you know gives us a vector. So when we've isolated this term on the right by doing this subtraction, we know that we have a vector on the left and we have a known vector here that's not equal to 0, and that in turn tells us that the remaining factor has to be a tensor. So the simple application of the quotient theorem tells us that b alpha beta is a tensor. Okay, well, it's got two indexes, and that of course means that it's a second rank tensor. and we put the indexes on the bottom. So in this form, it's a covariant tensor. All right, then next thing, let's consider this. Let's rename, you can see this just by discussing it. We don't have to write it all out. Imagine if we rename alpha to beta and beta to alpha. Then we would switch alpha and beta to the opposite order, and that would switch the order of it here. It would be beta alpha and beta alpha there. But you know from previous discussion that with this kind of partial derivative, the indexes are symmetric. The partial derivative of S alpha with respect to S beta is the same as the partial derivative of S beta with respect to S alpha. So flipping the indexes doesn't change the result of this partial derivative. And we used that kind of logic back in, I guess it was video 28, to show that the lower indexes of our Christoffel symbol are symmetric. Well, the same kind of logic leads us to the understanding that these two indexes are symmetric in this position as well. So we have a tensor. It's a second-rank tensor. It's covariant, and the indexes are symmetric. Okay, and finally, consider this, that we know from the original discussion that this part of the expression works by itself for a plane. So what we're going to do now is to consider this as the general expression for a surface manifold. It's just that for a plane, when we have a plane, we know that this part of it's all we need, which means that this B alpha beta is 0 in order to represent a plane. So with that having been said, we look at this as the general expression for a surface manifold, and a plane turns out to be the special case when B is equal to 0. Okay, so where does that leave us? What do we do next? Well, let's do this. Back in video number 29, if you recall, we formed the dot product of both sides of this equation with our contravariant basis vector Zm like this. And when we took the dot product on both sides like that, you'll recall that it led us to this understanding. You know, when we do this dot product, this is a delta function. It absorbs the k index, makes it m, and so we're able to solve for our Christoffel symbol in explicit form to look like this. So the next thing we want to do is to perform a similar operation down here to see what happens next. Let's see what happens when we form the dot product of this expression with the contravariant basis vector. Okay, so what we do is we take the dot product. We'll use S lambda in the upper position here, and we will dot that with the left side of the equation here, partial of S alpha with respect to S beta. And of course, I've got to do the same thing throughout the equation. So on the right-hand side, we'll have Christoffel symbol gamma omega alpha beta times S omega dotted with S lambda. And of course, we have to use that with the last term as well. So we have B alpha beta times n hat, again dotted with S lambda. Okay, now something very interesting happens here. First of all, this factor right here becomes a delta lambda omega, and the omega index here is absorbed, leaving us just with lambda here. So this whole term resolves down to gamma lambda alpha beta. And in this term, remember that our basis vectors lie in the tangent plane, and therefore they are orthogonal to our normal. So the dot product here is just 0. This whole term drops out. And that means that this entire right-hand side of this expression resolves simply to gamma lambda alpha beta. Okay, and that's good news because that means we can switch sides of the equation and do some renaming to come up with this expression. We would have gamma alpha beta omega, And if we rename the indexes the same way on the other side, that's going to give us S alpha dotted with a partial of S beta with respect to S omega. And I'm sure you see it, that means this form right here, this one, is exactly the same form as this, just using surface coordinates instead of our z coordinates up here. So the point of the exercise is this, that even though we have an expression up here that is different than this expression, in other words, we had to modify this to get this, when we form this dot product, the result right here is the same in both cases. And this turns out to be a really big deal. And the reason is because if you remember, when we started analyzing the Christoffel symbol, we started looking at things like his transformation rule. We looked at Christoffel symbols of the first and second kind. We derived expressions for evaluating the Christoffel symbol. We based all of that on this form in videos 29 and 30. We didn't use this one, we used this. We started here and derived all of those properties of the Christoffel symbol. Well, that means that those derivations apply down here equally well. In other words, we don't have to redo any of the analysis for the Christoffel symbol. Everything we did in videos 29 and 30 continue to work. So here's kind of the takeaway of the video, that even though we realize now that we have to rethink what the Christoffel symbol actually does for us, we wind up with this expression in both cases. So we're motivated to do this, and that is to think of this as the definition of the Christoffel symbol. And by using that definition, it continues to be the same in all cases. For all manifolds, we can define the Christoffel symbol using this relationship. But what we have to do is to understand that the application of the Christoffel symbol is different. For a Euclidean space, this is the application. It's the simple linear combination for our partial derivative. In this case, for the surface, the Christoffel symbol is used as the linear combination of the surface projection only. So this relationship only represents the surface projection, and we need this extra term out here. So that's the major takeaway of our video and what we've done here. Now we've got more ground to cover on this topic, but before we do, I want to take a break here for a brief review of what we've done so far before we continue on in the next video. The first thing we did in this video was to show that even though this expression by itself is valid for a plane manifold, it is not sufficient for a curved surface in general. In order for it to be valid for a curved surface, we have to add this term right here. What we're in effect doing is saying that this relationship, the partial derivative of our covariant basis vectors, may result in a vector that points in any direction, not just a vector that lies in the tangent plane. So, to represent it generally in our tangent space, we have to have a term for our surface projection and the normal projection like this. Now, in the process of doing that, we introduced this new term here, which we said was the curvature tensor. And we also derived the fact that the curvature tensor is a second-rank covariant tensor, and that it is symmetric. We can switch indexes alpha and beta. And finally, we recognize that the value of our curvature tensor is going to be 0 if we are indeed representing a simple flat plane as a manifold. All right, now given all of that, we then took the dot product of both sides of this with a contravariant basis vector, and we found out, first of all, that we derived an explicit relationship for our Christoffel symbol for the surface. And it turns out to be identical to the form that we derived back in video number 29 when we analyzed the Christoffel symbol back there. And as a result, that means that all of the properties that we derived back in videos 29 and 30 continue to be valid. So for reference, I have listed them here. We have the transformation of the Christoffel symbol, that remains valid. We found that The Christoffel symbol of the first and second kind are derived and defined exactly as you see here, just like they were back in videos 29 and 30. And then we have the partial derivative of our covariant metric tensor, simply equal to the sum of these two terms. And from that, we're able to derive explicit forms to evaluate the Christoffel symbol either in the first kind or the second kind. So all of these things remain valid because of this relationship right here. In the next video, we'll pick up where we left off and continue on with our analysis of the Christoffel symbol as it relates to surfaces and curved manifolds.